Have you ever wanted to be a detective? Cracking a really tough case? Well, today, that's exactly what we're going to do. But our crime scene is a beaker, our clues are just a bunch of data points, and our case file, it's a real question from a university chemistry exam. So, let's dive in.
So our case kicks off with a kind of chemical identity crisis. We've got this substance, ammonium cyanate, and when you dissolve it in water, it just spontaneously starts rearranging its own atoms to become something totally different, urea. We're talking the exact same atoms, just in a new configuration. It's a classic chemical whodunit, or maybe more of a howdunit and how fast.
And here it is. This is our official case file. Question 4, straight from a final exam for a general chemistry course. This is no hypothetical. This is the real deal. Students were handed this set of data and asked to unravel the mystery of this transformation. And today, well, so are we. Okay, every good investigation needs a clear mission. Ours has 2 parts. First, we've got to figure out the rules of the reaction, what chemists call the reaction order. This basically tells us how the speed of the reaction is connected to the concentration of our chemical. And second, we need to find the specific speed of the reaction, its rate constant. How fast is this thing really going? Here's our evidence. This is everything we get. A table that tracks the concentration of our ammonium cyanide over 150 minutes. You can see it starts at 0.38 molar and just steadily drops. These numbers, right here, are our only clues. The entire solution is hiding somewhere in this pattern. So how do we get these numbers to talk? We can't just stare at them and hope for the best. In chemical kinetics, what we do is we test hypotheses. We're going to line up the usual suspects, the different reaction orders, and see which one's story actually matches our evidence. It's a classic process of elimination. Our first suspect is what's called a zero-order reaction. Now, if this were the case, the relationship would be super simple. The concentration would just drop at a perfectly constant rate. If we made a plot of concentration versus time, we should get a perfectly straight, downward-sloping line. So, does our evidence fit this story? Nope, not even close. Case closed on that one. If you actually plot the raw numbers from our evidence file, you get a curve, not a straight line at all. The reaction clearly starts off fast and then slows down as it runs out of fuel. Suspect number 1 is officially eliminated. All right, on to our next suspect, a first-order reaction. This one's a little more complicated. We have to look at the data through a different mathematical lens to see if we can turn that curve into a line. For this to be our culprit, the natural logarithm of the concentration, when we plot it against time, that should give us a straight line. Let's see if it works. And strike 2. We run the numbers, plot the natural log of the concentration against time, and we get another curve. It's closer, for sure, but still no cigar. The evidence just doesn't support this theory either. We're running out of suspects, which, usually means we're getting pretty close to the truth. Which brings us to our third and final suspect, the second-order reaction. This is our last shot. The test for this one is to plot the inverse of the concentration, that's 1 divided by the concentration, against time. If this gives us a straight line, we have found our culprit. Okay, let's plot it. We take our data, we calculate the inverse for each concentration point, and we plot it against time. There's the first point, the second, the third. Look at that. Just look at it. They are all falling into a perfect line. This is that moment in the detective show where the final clue just clicks right into place. And would you look at that? It's a perfect straight line. The data fits the second-order model like a glove. We've found it. We've cracked the first part of the case. The reaction follows second-order rules.
So what does second order actually mean? Well, it means the reaction speed is incredibly sensitive to concentration. If you double the concentration of the ammonium cyanate, the reaction doesn't just go twice as fast. It goes 4 times as fast. The rate is proportional to the concentration squared.
Now remember the second part of our mission. We needed to find out exactly how fast this reaction is. And that beautiful straight line we just found, it does more than just identify the suspect. The slope of that line is the answer we're looking for. It's the rate constant, that magic number we call K. So what's the value? When you calculate the slope from the graph, we find that K, our rate constant, is 0.0597. And the units tell us exactly how concentration and time are related for this specific reaction. This number is the precise speed limit for this chemical transformation. And with that, we've solved the first two parts of the exam question. But wait, there's one more piece of the puzzle the exam asks for, the half-life. It's a concept you've probably heard of, right? Especially with radioactive decay. It's really simple. It's just the time it takes for half of your starting material to disappear. And now that we know the reaction order and the rate constant, we can actually calculate it. And the calculation is surprisingly straightforward. There's a specific formula for the half-life of a second-order reaction. We just need to plug in our rate constant, K, and the initial concentration, which we know from our evidence file was 0.38 molar. A little bit of arithmetic, and we'll have our final answer. And there you have it. Case closed. We figured out the reaction as second order. We established its rate law, we found the precise rate constant, and we calculated its half-life, 44.1 minutes. We have successfully solved question 4. So why does any of this matter? Because what we just did, using data to figure out the speed and the rules of a change, is fundamental to pretty much everything. It dictates how quickly medicine works in your body, how food cooks in an oven, how batteries store energy, and even how pollutants break down in the environment. It's not just about passing an exam. It's about understanding the timing of the universe. In the end, we cracked this case not because we had more evidence, but because we knew the right way to look at the evidence we had. By just transforming the data, we revealed the straight line that was hiding there the whole time. It makes you wonder, doesn't it? What other profound truths are just sitting there in plain sight, waiting for us to find the right perspective?